Before we start with today's webinar, I would like to advertise a future event, which is the ESRF ILL Colloquium on 27th November by Neil Ferguson Imperial College London on the dynamics of COVID-19 pandemic. I give you a few technical information concerning this event. It is broadcasted to you via Zoom and on YouTube, and it will be available for replay on YouTube. You can contribute to the discussion by using the question and answer box, which you find on your Zoom interface. And you are invited to use this to raise your questions during and after the talk, and also to upvote the questions of other participants that you think should be answered in priority. I would like to point out that this series of events is supported by the Streamline project of the European Union. I come now to the introduction of today's speaker, who is Marius Retegan. Marius studied chemistry at the University of Cluj-Napoca in Romania, and then at the Université Joseph Fourier in Grenoble, France. He got his PhD, received his PhD in 2009 from the Université Joseph Fourier in chemistry, and then had a first postdoc in Grenoble until 2011, and a second postdoc from 2012 to 2015 at the Max Planck Institute at Mülheim an der Ruhr. And eventually in 2016, he joined the ESRF as a scientist. The title of his talk today will be Computational Spectroscopy in the Age of the Extremely Brilliant Source, from punch card to artificial intelligence. Marius, please.
Okay, so is it okay? You see my presentation, I assume? Yes. Okay, thank you, Patrick, for the introduction. So as you mentioned, today I will be talking about the computational spectroscopy in the age of the extremely brilliant source, a little bit of history, how this was done in the early days, and to the present day, where we are starting to see more and more use of artificial intelligence. Of course, because we are I'm working at the synchrotron today. I will be talking about X-ray spectroscopy, which is an element selective probe of the oxidation state, geometrical structure, and chemical bonding around some absorbing atom. This is X-ray spectroscopy is one of the most prevalent techniques at the ESRF, and there are quite a few beamlines that are dedicated to this technique. Among them, X-ray absorption, as you can see in this table, is present on almost all of them, but we see more and more emergence of this photon in, photon out spectroscopy, which seem to gather momentum in the recent year. Experimental X-ray spectroscopy, the data from this is often evaluated by comparison with the reference compounds. So, for example, if you're interested in measuring an iron sample, at the same time with your compound, you would measure a set of reference compounds, and in this case, iron oxide, for example. And the next step would be to compare the spectrum that you got for your sample with the series of spectra of these references. Based on similarities between the references and the spectrum of interest, you would be able to say something about the oxidation state, for example, of the local coordination environment. This is the so-called fingerprinting approach. You're using the features of the spectra, but you don't necessarily understand or try to understand the origin of this feature, the structural origin of this feature. Computational spectroscopy tries to go a little bit further and to to maximize the amount of information that you can extract from the experimental data. So it tries to answer the question related to what those features are and how are they related to the structure. These are, of course, the domain of calculation, and there exist a number of codes that can be used to do computation, X-ray spectroscopy computation. I divided them here in 3 categories. And first, you have the specialized ab initio codes. These are codes developed specifically to do such calculation. Then you have more generic ab initio codes. These were not developed to do X-ray spectroscopy, but they do provide, or they had over the years have this type of techniques have been included. I think among the list of software that I present here, Orca clearly stands out because it's probably the software that has the most, the largest number of methods that can be used to perform such calculation. Finally, we have the semi-empirical multiplet codes. Historically, these have been the most used codes to do X-ray spectroscopy. This is because their nature of modeling the system using a parameterized Hamiltonian, they are fast and they were used for very, very long time. Actually, the first use of these codes was to do atomic spectroscopy, and they rely mostly on calculation using the so-called Cohen code. It has now more than 50 years and has seen an immense impact on the atomic physics community. In the early days, these calculations were done using punch cards. These punch cards are perforated pieces of paper that were stuck together in order to get the program that was actually doing the calculation. The scientists would go to a computer room and run these calculations. This was a very tedious process, and if lucky, the scientists could run 2 or 3 calculations in a day. But even so, the importance of having this type of calculation to be able to understand experimental data was clear from the beginning. To the X-ray community, these calculations came a little bit later. And I'm showing here 2 examples. First is trying to understand the ground state electronic structure of manganese in different type of metals. And the second is the calculation of X-ray absorption spectrum for lanthanides, in this case, cerium. Of course, an atomic representation of lanthanides can provide a reasonable good spectra. So it's known that lanthanides do not necessarily interact strongly with its environment. But this is not necessarily always the case. So a natural step was to go beyond atomic multiplets. And you have here a representation of a crystal structure. And you see that the absorbing atom is surrounded by a number of other atoms, his neighbors. So electrostatic influence must be felt by these absorbing atoms. In addition, you can clearly see that the orbitals which are localized on the absorbing atom will hybridize, will interact, if you want, with the ligand atoms. So this type of interaction simply cannot be excluded if you want to get a realistic picture of the system. And indeed, including crystal field interaction, or going further, including hybridization in the system, have proved to be essential in explaining the spectra for transition metals, for example. I would just like to say that multiplet simulation were also instrumental in the development and validation of magneto-optical sum rules. These were rules that were developed by Teo Tolle while he was visiting the SRF, together with Paolo Cara, Francesco Sette, and Massimo Attarelli. They provided a simple way to link the absorption intensities of the intensity of X-ray absorption spectra and XMCD spectra to the expectation values of the spin and orbital momentum, orbital angular momentum. their simplicity has made them very applied a lot in experimental by the experimentalists. So it's not surprising that these two papers actually gather well above 2,500 citations each, and probably are to the day one of the most cited papers that came out of the SRF. Of course, behind these theoretical developments was code, and started with the Cohen code, which Tolle and his collaborators extended later. But these were difficult to use codes, and even more difficult to modify. So it's only natural that in the recent years we've seen a lot of new codes appearing, and among them I would just like to point to the Quanti code, which is developed by Maurits Haverkort and his collaborators at Heidelberg University. This provided an up-to-date way of doing such calculations. Quanti is a library. It's a very powerful and it's a very versatile library. But one thing that you still have to do when to do this calculation, you have to write some code, even though in some cases it might not be a lot, but you have to write code. This can be a high entry barrier for most scientists that are not necessarily experts in the field. Also, the program is very forgiving, and even for an expert is very difficult to spot an error. So it's the possibility of doing wrong calculation is very real. So you really have to be careful, and you really have to know what you're doing with this code. So a natural step to bring this software closer to the community was to package everything into an easy-to-use software. And this is how CRISPy was born, which is a software to do exactly this computational spectroscopy, but for the user that don't necessarily have a background in such calculations. It's written with Python. It has it takes advantage of all of these powerful Python libraries, and it already can do quite a lot of calculation for transition metal lanthanides, different type of experiments, a large number of edges and symmetries. I think that one advantage that CRISPy had is that from the beginning, and it helped a lot with the adoption, is that from the beginning it provided an easy way to install on Windows and macOS. And and more recently, this was also extended to have a Jupyter Notebook interface that I'm going to say a little bit more later. So, as I said, it already covers quite a lot of calculation, but I just want to showcase two examples where more advanced features of the interface. Most of the things that are measured on the spectroscopy beamlines do not necessarily have let's say, a high symmetry absorbing site. And if you measure biological samples, or if you measure molecular compounds, this is certainly going to be the case. So I just want to, so in principle, for biological samples such as photosystem 2, which is a protein that does water oxidation, and which has as its center a number of metallic atoms that do all this catalytic reaction, and they change oxidation state and they change coordination number. It's going to be very difficult to deconvolute the X-ray absorption spectra or RIX spectra by relying solely on classical calculation, if you want. Rather recently, a few years ago, from the group of Marianne Ario and Amélie Juin, there was a very nice paper that came out where they show that in sites that lack center of inversion, like in this case a tetrahedral, in addition to the quadrupolar transition, the dipolar transition would participate in the final intensity of the spectrum. So what you have here is that it's not necessarily the quadrupolar part that gives you the final shape of the spectrum, it's actually the dipolar part. Now, such calculations are and were at the time the state of the art, but with the recent developments, it's possible to run this calculation directly in an interface. So What you have here is the result of such a calculation with the quadrupolar part here, the dipolar part here, and their summed contribution. Another field that has been significantly impacted by the use of X-ray spectroscopy was the derivation of crystal field and covalency parameters in the case of 5F elements. And this is from the work of Kristina Gvashnina and Sergei Butorin, where you have the experimental spectrum measured here, and below it, simulation using an Hamiltonian having different levels of approximation. So starting from the atomic representation of the system, going to a crystal field where we actually consider just electrostatic interaction between the neighbors and the absorbing atom, and the charge transfer, which is a way to say that now we are taking also the surrounding atoms into our account. And it's only using this charge transfer that we're able to actually reproduce the high energy side of the spectrum. As with the previous example that I've shown, such calculation can be now routinely performed in the interface. Here I represent the three spectra, the atomic, crystal field, and what I call the ligand field calculation, one on top of the other. So you can easily perform this such calculation with an interface. I think having an interface is clearly offers great advantage for a user that is not necessarily familiar with such these tools. But in the recent year, or like starting with the EBS upgrade, ESRF is going to transition to a new paradigm for online and offline data analysis. So this is going to be based on the so-called Jupyter Notebook. And some of you might be familiar with, but briefly, is just a way to do your data analysis directly in your browser. ESRF is already providing such a hub where you can connect to your experiments and do everything in terms of data analysis easily in your browser. For spectroscopy, for data analysis for spectroscopy, there exist already a number of tools that can be used. For example, many of you are familiar, I'm sure, with PyMCA. This is a tool that is essentially helps you do data reduction on the beamline. But maybe not every one of you knows that such PyMCA can be also easily used in a Jupyter Notebook interface. There's also Large, developed by Matt Newville in the University of Chicago. Slot, which is a software developed here by a scientist here, Mauro Rovezzi, but also the Silex library. I think these are fantastic tools, but for the moment, I'm under the impression that they are somehow underutilized in the case of the Jupyter Notebook. In what concerns calculation, we have the atomic simulation environment. This is a project that tries to bring the computational tools that some of the programs that I even showed before and in the introduction directly into this environment. This is not an easy task, and most of the things that have been done until now are related to geometry optimization and molecular dynamics, for example. So spectroscopy kind of took a second seat, but hopefully this is going to change. Now, because CRISP is developed in Python, it's rather straightforward to bring it to the Jupyter Notebook interface. So with the recent version, this is actually quite possible. And I would just want to show you a brief example how this can be used in the Jupyter Notebook. So I'm just going to start a pre-recorded video. So first, I'm importing from the library, I can call it that, a function that allows me to set up a calculation. I'm going to do calculate iron in a C3V symmetry, and I'm going to do just L to 3H. Now, by default, the program is only going to do the isotropic absorption spectrum, but in this case, I'm also interested in the circular dichroic. Of course, if I want to do dichroism, XMCD, I also need a magnetic field. I'm going to also add some Gaussian and Lorentzian broadenings. So next we have the setup of the Hamiltonian parameters with some crystal field parameters and some scaling factors. I can list all these parameters. You can see there are quite a few. a bit scary, I would imagine. Then once the setup is done, I can start the calculation in the notebook. It's going to take a few seconds, so it's not a very involved model, so it's going to be quite fast. After this, I can look at the output. The output is rather short, but I think it provides essential information. In this case, the expectation values of the spin and orbital angular momentum operators is there, so it can easily compare with experiment. Finally, I can plot the spectra. Of course, in this case, I've stopped the analysis here, but you can easily imagine that you can start loading experimental data, you can overlay the two, and then try to optimize the calculated spectrum to fit the experiment. So this is a next step in what concerns spectroscopy calculation. But we have to look ahead. ESRF is now in the extremely brilliant source stage, and most of the experiments are going to see an increase in data flux and also increase in speed. The first instinct would be to just keep calm and collect more data, but I think depending on the technique, sooner or later we're going to be overflown by this amount of data that's going to be left unanalyzed. And so we have to find a way to substitute all these complicated, sometimes calculations, with a more automatic workflow. In this respect, machine learning has emerged recently as a way to map this complex nonlinear relationship. So it has touched many subjects of research, such as rechargeable batteries to study the diffusion of ions or their mechanical properties, solar cells, conversion efficiency, calculation of band gaps using DFT, or the discovery and development of catalysts. And it's actually in this last point that the X-ray spectroscopy plays a very important role, as it is highlighted by these two recent reviews. The machine learning landscape can be quite scary, and it's quite complex. But we recently see that neural networks seem to be more widely used, at least in what concerns spectroscopy-related studies. So in the next part of my talk, I will just try to present you the state-of-the-art and some recent efforts that were done here at ESRF. The first thing that you can do with the machine learning model is to predict the X-ray spectrum. This is work from Thomas Penfold's lab, and you can think of the use of neural network here as a substitute for your friendly computational program. So what they did was to feed into this neural network a certain representation of the system, either a Coulomb matrix or this radial distribution curve, and to get out the X-ray spectrum. The results were quite nice, and in the best case scenario, the machine learned spectra, which are the black curve, so the intense black curve, overlap entirely with what is predicted from DFT, which are the light gray behind them. Even in the worst case scenario, where there are large deviation between the intensity of the DFT calculated curve and the one predicted by the neural network, we can see that the shape of the spectrum is actually captured quite accurately, and it's the intensity that seem more problematic. Similar results were also published recently related to the oxygen and nitrogen K edges. What is different from the previous study is the way the 3D structure or the coordinates were featurized and fed into this neural network. And again, even the best decile and the worst decile spectra, we see that the agreement is actually quite good. So this is the prediction part, probably the more difficult part. we can also use machine learning to go the other way around. So we give the X-ray spectrum to the model, and what we get out are structural and electronic parameters. For example, here in the case of this metal organic framework that does absorbs CO2 on the nickel side, the authors showed that different machine learning approaches can provide very good structural parameters, like the nickel absorbent distance or the angles. So they can be quite successful in getting those parameters. A more extensive study dealt with, in addition to looking at regression, which means getting a very specific value out of this neural network, also with classification. So in this case was the full 3D row. And what the authors did was to train a network using DFT calculated spectra, and to see how it performed in getting out for the coordination number of the absorbing atom, some atomic charges, or the distance to the neighboring atoms. We're also interested in applying machine learning for spectroscopy. In this particular case, it was related to the oxygen cage exhaust spectrum. And the spectral features, while we have these three features here, are sensitive to the structural distortion as the orbitals are polarized towards more polarized towards the hydrogen atoms. The neural network used was developed was using the standard libraries of machine learning, TensorFlow and Keras, and the optimization was done using using this Talos library. So the hyperparameter optimization of the neural network, number of layers, number of neurons, and so on. The training data was, Christoph Salle was grateful in providing this to me. So they were basically a number of 10,000 oxygen cage spectra and the corresponding structural parameters. So the train network actually performed very nicely, and we were able to get inference of certain structural parameters well below the error that would be required in day-to-day application. We also tested the use of the entire spectrum or the use of region of interest, so the integrated intensity in each of these regions. And somewhat, so not unexpectedly, using the full spectrum provided a better, provided a lower error for the inferred parameters. So what I presented until now was related how neural networks can reach the same level of accuracy as a DFT. So the ground truth, if you want, the goal was to reach the DFT accuracy. Of course, we want to do more with this. We want to feed to these networks experimental spectrum. So what you have here is an experimental spectrum in blue and a calculated one below. So the goal is to find a way to measure the so-called distance between these two spectra. And there are different ways to do this. There are different formulas to calculate this distance. And this was for example, study. These different distances were studied recently, and how robust they are with respect to Gaussian broadening, for example, or signal-to-noise ratio. So you see that let's say a robust distance would have to stay close to 1 as much as possible. And in this case, the authors found that Pearson correlation coefficients, it is the most robust against spectra broadening and noise. In the similar idea was also actually published earlier, where an algorithm was proposed to identify absorption spectra, KH absorption spectra for transition metals. So we started from a measured spectrum, which then would the species, absorbing species would be identified, This would be fed to a database, a lookup database, and from this, the spectra of the corresponding method would be taken out, and they would be ranked using so-called weak learners, so a number of learners, and well, ultimately this would be combined to give the probability that a given calculated spectrum is the experimental one. These are some results for in this case, the aluminum K-edge and the 4 highest ranked results. As you can see here, it manages to get the oxidation state, but has some, and in this case also the lattice parameters. But in the case, for example, of vanadium, in this case seems to be more complicated, so the lattice is not. However, the authors tested this on 19 spectra, and they got valid prediction quite in quite a lot of these cases. So while this is certainly does not reach the level of accuracy that we want, it's certainly a very big step forward, considering all the things that contribute to this comparison, like peak shifting and similarity measurement, noise, and so on. So machine learning can and probably will start to be used as a substitute for computation. This is not going to be universal, but there are going to be specific cases where then this can happen. And the big advantage of machine learning models is that it's about 4 to 5 orders of magnitude faster than a DFT calculation. Of course, this opens the door to integrate machine learning models into the acquisition pipeline, because you're able to do on-the-fly data analysis because you have sub-second inference using this pre-trained model. And at DSRF, the control system that is put in place is ideally suited for this because it's written in Python, and it's extremely easy to integrate such models into the pipeline. Of course, DFT is not by no means the best theory to calculate spectrum. So accurate improvement of the theoretical simulations would be easy. It is strongly desired, but already at the DFT level, these calculations can be quite time-consuming. So recalculating everything using some high-level theory is going to be very, very difficult. However, there are known ways to overcome this limitation. And this is an example where, a recent example where a network trained using DFT data, this is the energy of some conformers of simple organic molecules, was retrained by using a smaller amount of a smaller data set calculated at this coupled cluster level of theory. So the neural network was not entirely optimized. This smaller subset was only part of it. In this case, the central part that was optimized. And the results were quite impressive. So in the end, the neural networks was able to get coupled cluster accurate energetics in under a second, of course. In what concerns the calculation of spectral function using coupled cluster, we're not there yet. There are from a few labs, there are clearly new improvements coming, but for the moment, all this calculation using coupled cluster are done for relatively small molecules. So it might take some time before these are going to be routinely applied. Especially, I would just like to mention the work from the Nese lab and Manganas. So ESRF is engaged in providing frictionless and human-centered tools that help the user community to analyze their data. I think with CRISPy, we are able to bring this multiplet simulation closer to the experimentalist. this is the website where you can find the latest version of the program. So if you are interested, I would encourage you to visit it. There are still things to do, in particular to try to bring more of the more spectroscopy simulation to the Jupyter notebook. This is going to be very important and is going to facilitate a lot the generation of supporting materials, for example, during the beamline proposal. And what concerns machine learning, I think we are moving. We are going to see is going to be the next leap forward. And as computation become totally abstracted from the user, and machine learning substituting basically the expert that you're used to having at your side when you're doing your measurements. In addition, I think they're going to also be crucial in decision making during experiments. So you're not going to have to wait for the simulation when you go home. You're going to have the answer while you're measuring. With this, I would like to acknowledge all the scientists at the SRF, ID26, ID20, ID32, and ID12. The data analysis unit that is responsible for the development of this fantastic CLEX library, the external collaborators that I had the pleasure to work with, of course, the CRISPy users and the contributors. And I would like to thank you for your attention. I will be very happy to take any questions that you might have.
Thank you very much, Marius, for this very interesting presentation and survey of the possibilities of spectroscopy analysis at CSRF. So now the talk is open for discussion, and I invite you to ask your questions. I remind that you are invited to use the question and answer box, which is at the bottom of your Zoom window. And we start with a first question concerning machine learning. A question is by Sami Yohani Vazala. What kind of learning data does the machine learning model require? Question. A lot of spectra of well-known standard materials? Question mark.
So the training data, because the amount of data that is actually required to train a machine learning model, all the data that is currently being used is computational data. So it's data derived from computation. It's at the current state, it's impossible to use experimental data to train these models, because there is no enough curated data to do this. And experimental data poses a lot of additional problems, because while you can have the experimental data, you have to have also the accompanying parameters that go with it. So you would need to know precisely what the structure is. So what is the coordination of your absorbing atom? And very often in experimental data, you have contributions from, let's say, sites that have different oxidation state, and you cannot simply disentangle the two. While in computation, you can just select the site that you're interested in, and you're going to have the spectrum of that site. So that's, for the moment, we rely on computational data.
Thank you. We have another question from Kirill Lomachenko. Training of the neural network is often a challenge when it comes to X-ray spectroscopy, because one has to know the correspondence between the spectral features and the structural parameters for each member of the training set. Could you please elaborate how this problem was solved, for example, with the oxygen spectra that you have shown?
So in the case of oxygen spectra, actually is not that complicated. Of course, is Christoph Salle that did the mapping or the calculation of the spectra. So, and even I think he's using this data in another machine learning project himself. I think I don't see necessarily the complication in that, because you have the 3D coordinates of water molecule, and then you calculate the spectra for those coordinates. So you have the input of the computational program, you have the structural parameters, you have everything available, And then what you get from the you get out is the spectrum. So the mapping between structural parameters and spectrum is very straightforward. The complication, as I said, comes when trying to do this with experimental data, because there it's not that easy. I don't know if, I hope I answered this question, but I actually don't necessarily see such a challenge in connecting spectra to structure when you're using computation.
Thank you. We have a comment more than a question from Frank de Groot, which is X-ray absorption spectra are affected by many experimental artifacts like self-absorption, phanobroadening, and second harmonic X-rays. Can you comment on this point?
I assume is related also to this part of the talk with the machine learning part. So I think what's important here is the finding ways to have this similarity measurements. Of course, experimental spectra are noisy; they have a lot of issues, and the capability of a neural network is going to be related how well the similarity between the calculated and the experiment is going to be. I think that there is only a certain amount of let's say of these annoyances that can be absorbed, if you want, in the neural network. So as soon as you go too far, or like you have too much noise in your experimental spectrum, then the neural network is not going to be able to do anything with that to extract the parameters. So the human might still be the best let's say model to do this.
Okay, so that seems to answer the additional question by Frank, which was, could this be put into a machine learning tool? Okay, you've commented about that. We have another question by Elisabetta Suturina. Is it possible to retain a nearest neighbors that was originally trained with DFT with a subset of experimental data instead of coupled cluster in the context of X-ray spectroscopy?
Sorry, to retain? Maybe I can also look.
And I guess it was, well, don't know what NN means in the question, in the context. So maybe we need to ask Elisabetta to reformulate her question. We have a question from Ennio Capria. AI would just help us to run a faster data analysis than what is already made with DFT, or could be also possible to go beyond in terms of information gained? In other words, is it all about speed or about quality of the data outcome?
No, it's mostly about speed, because these networks are trained with DFT, so you cannot get better answer than a DFT. But the fact that you're going to be able to get these answers while you're measuring, I think this is the crucial part in all this. So, as I said, traditionally you would measure some spectra and then you would go home and try to analyze them. And sometimes the questions that you try to answer are very simple. What is the coordination number? What is the charge? What are my neighbors? How far are my neighbors? But having a model that is actually in the pipeline, in the measuring pipeline, is going to give you, to a certain degree of accuracy, the answer there while you're measuring. So this can help you to change and modify things while you're measuring. I think this is going to be a great, is going to change a lot the ways the data are analyzed.
Okay, maybe we can come back then to the question of Elisabetta. Is it possible to retain a neural network to retrain a neural network that was originally trained with DFT with a subset of experimental data?
Yes, it's exactly what what it was shown in this study. So the neural network initially here was trained with DFT to get DFT-like energies out, and then you see that they used 5 million data points. And then they went to this couple cluster approach, and they used a tenth of so a tenth. The set was 500,000 data points. So what they did was to fix part of the neural network and retrain only partially the network using this subset. So, and in the end, this proved to be a very good way to get couple cluster energies from a neural network.
Thank you. Maybe I would like to ask another question on a slightly different point, which is the multiplet is essentially a theory for an atom or an atom in some environment. Essentially, so this is for localized electrons, and there are plenty of materials in which electrons are not localized on an atom. Itinerant materials or metals, and many of the interesting correlated systems are in between, not really localized, not really delocalized. How can we incorporate this into a method that is based upon multiplets? Is it possible to be quantitative?
It's funny because a while ago I was having a discussion with a scientist here at the SRF, and he was saying that we're just talking about the paper where he was saying that yes, these long-range interactions are very important. Then they were using multiplet to do exactly to study as if it would be a localized process. I think so. It's a bit yeah. We have iterant effects, but in some cases, then you go back to trying to calculate the spectrum using local methods. I haven't worked on this specific aspect, but I know the work of Maurits Haverkort, for example. He's specifically working on trying to describe spin waves and charge waves using multiplet simulations. I cannot really comment more in details about this because as I said, I'm not really in this field, but he showed the last time we had this Quanti workshop, he showed the possibility of having calculation done with Quanti for such systems. So yes, it's possible to have a local description of the system that then can extend to cover these iterant effects that you mentioned.
Okay, then there is a related question by Andres Cano about the correlation effects beyond DFT. And the question of Andres is there a chance that they can be better understood thanks of machine learning?
So understanding correlation beyond DFT. So I think machine learning has this problem that that you get an answer, but most of the time you do not know what the model is using to get you that answer. So it is a black box, and there are ways to try to, for example, to get more out of, like to see what part of the spectrum was important to get me correctly the coordination number. And this is something that was done in this study, where instead of feeding to the machine learning model directed the spectrum, they were using polynomial feeds of the spectrum, which were slicing to different parts of the spectrum. So I think if you want to understand, so to go back to the question, I think if you want to understand correlation, we have to give to the machine learning, to package the input to the machine learning in a way that we can see in the output what exactly was given in. So basically to try to, in a way, to separate these correlation effects a priori, and then to see what the machine learning does. For Spectra, it's were quite interesting, the results that they obtained, because they were able to say, yes, it's actually the pre-edge that is more important to determine the coordination number. But like to go as far as trying to say more about correlation effects from DFT, it's not going to be an easy task.
Beyond DFT, yeah. Okay, thank you. We have a question from Eduardo Machado Chari. Must the DFT training data be generated by the same code? And what is the accuracy of the network using DFT plane wave results with respect to atomic orbitals?
Most of the studies use the same code because it's easier to build the pipeline that gets you the spectrum out. In the end, what matters is how well does DFT or any other code, how well is able to get to the experimental spectrum. So it doesn't matter if you're using plane wave DFT or atomic centered orbitals or something like that. In the end, what is matter is the spectrum. So what is the final spectrum? How well do you manage to get the final spectrum? Now, it's an important thing here to mention that these calculated spectra are sticks. So you have an energy position and you have an intensity. So there is a lot of under the hood. Even if you're calculating with DFT, if you're calculating with other more advanced methods, you're going to have to broaden the spectrum. You're going to have to shift the spectrum. So there is a lot of uncertainty when comparing experimental and DFT calculated spectrum.
Thank you. We have now a question by Alexei Bubnov. Calculated spectra do not always accurately reproduce all the features observed in experimental data. Are these not perfect calculated data still useful for training neural networks?
Yes, for training neural networks, of course they are, but that neural network is always going to be perfect or is going to be useful in trying to get out or in trying to predict properties on synthetic data. So the neural network is only going to be very good at predicting synthetic data. So you train with DFT, you feed DFT in, and you get probably something that is good out. So this is why I think these studies where we are having similarity measures are very important, like to see what is the effect of changing the broadening on your spectrum? What is the effect of having more noisy experimental spectra? This is extremely important going forward.
Thank you. There is a question by Michael Baker. Is there a plan to continue the development of CRISP to include more types of experiments?
I would. I hopefully. I think. Let's see. I hope is going to be the case. There are still things that can be done.
So what kind of other types of experiments could be incorporated?
So X-ray Raman, for example, and to have a closer look at the RICS calculation. There are still things that need to be done there, like to properly get, for example, an isotropic RICS spectrum out of the calculation. It's something that I think most of even the theoretical community do not necessarily use the cleanest or the clearest approach to do that. So I think there are definitely ways to improve or things to add.
Thank you very much. So I think we've more or less exhausted the questions. No, there is another question by Elisaveta Suturina. How important is the spin-orbit coupling for X-ray spectroscopy simulations?
I think of course, it's very important. I think she knows that, but it's extremely
to comment on it.
Yeah, she wanted. So it's no surprise that actually most of the examples that you've seen here in terms of calculations, with the exception of this one, which actually uses multiplet to train the network, all of them were k-edges of transition methods. So these k-edges of transition methods, you can kind of go without having to consider spin orbit coupling because you're dealing with an 1s orbital. Of course, when you move to soft X-ray and when you have like 2p core holes that are being formed, it's going to be fundamental to include spin orbit coupling in those calculations.
Okay. Do you plan, a question from Marianne, do you plan to combine CRISP and ORCA output?
That would be actually something that would be very nice to have because ORCA, as I said, provides such a wealth of methodologies that to calculate X-ray spectroscopies. I'm not saying something against ORCA, but I'm just saying that some of the post-processing it can be quite challenging, let's say, for an experimentalist. And again, nothing against Orca or experiments, but I think we can bring the two closer together. Yeah, so that would be actually something that was is planned.
Thank you, Marius. I think
Thank you.
we have now to close the discussion. So thank you again for your presentation and the discussion. I'd like to thank all the participants for joining us for this webinar and for contributing to the discussion. And I invite everyone to join us again in 2 weeks from now for the colloquium by Neil Ferguson on the dynamics of COVID-19, which is definitely one of the hottest topic currently. And with this, I thank you, say goodbye to everyone and have a nice weekend. See you soon.